Okay, welcome to the College of Southern Idaho, the Evergreen Building, my classroom. And this is going to be our first video in the series I'm going to put together on minerals. And just as a way of introduction, my plan is to keep it very basic, mainly focusing on minerals you might see in rocks. Some of you might be expert mineralogists. I am not. There's over 4,000 or so minerals. We're not going to get into all of them. What I think I'd like to do after this first video today is maybe focus on a dozen or so, the more common ones, how you can identify them in the rock, what their significance is, maybe a little bit about what they're used for, that sort of thing. And I'm hoping that will be helpful because that could be a springboard as we get into rocks, which is tends to be what you encounter out in the real world when you're out on hikes and in nature, but helping people identify rock types out when they're out on their travels and such. And that, for me, that's really rewarding because geology and the earth is written in the language of rocks and landscapes. And so the more you can understand what it's made out of and the earth materials that we're going to look at and understand the processes, and that really just opens your whole mind up to understanding the stories that are hidden in the landscapes and in the rocks themselves. So we're going to start today with a video looking at minerals, and I want to start with mineral properties. And so just to kind of get our bearings with some definitions here, I put together a real simple sheet here. So we've got elements. So elements are the basic building blocks of, this should be matter. I already have a typo, not matter, all matter. And so when you think about elements, you probably think of, just like in a lot of classrooms, the periodic table of the elements. And so we have all these materials. We're not going to get into them. That's chemistry, but things like oxygen and helium and magnesium and sodium and iron and gold and nickel and neon and carbon, all these sorts of things, right? So that's what an element is. Probably knew that already. And then what a mineral is a mineral is has a specific definition. So if we take combinations of elements, what we might call chemical compounds, and then they have a specific composition and a crystal structure, but they're also solids, they occur in nature. These are these things we call minerals. And so most minerals are made of combinations of minerals. So you can see quartz, which is a very common mineral. It's just made out of nothing more than silicon and oxygen. Calcite, which is an important mineral that we'll talk about, is calcium, carbon, and oxygen. And potassium feldspar, another one we'll look at, is sodium, aluminum, silicon, and oxygen in some sort of proportions, right? So that's what a mineral is. Minerals tend to be for the most part, homogeneous in their characteristics, meaning they're going to look the same. They'll have the same color and characteristics throughout. So one way you could tell a rock from a mineral is, does it have the same color and characteristics throughout? So these are all examples of minerals. We'll talk about some of these here in a minute. Versus if you look at a lot of rocks, you can see different colors, different textures. And so that would be your clue as to what's a mineral and what's a rock. Just the consistency of the texture and the material in it. If you're seeing lots of different chunks, stripes, that sort of thing, good chance it's a rock. And you should always probably start out with the assumption that what you're looking at is probably a rock and not a mineral. So we know what elements are, we know what minerals are. So what the heck is a rock? A rock would just be any sort of natural occurring aggregate of minerals. So if we take minerals, squish them together in some way or process, that material then is what we call a rock. So for example, granite, which is a common rock type, is nothing more than these minerals: quartz, potassium feldspar, plagioclase feldspar. Those are the essential ingredients. And then it may or may not have a little bit of biotite, a little bit of muscovite, a little bit of amphibole. These are all minerals, right? So that's the recipe, more or less, for that specific type of rock. Okay, and we'll spend time on the rocks themselves. So that's our good definition. Next, a little bit of homework here is we're going to focus on physical properties, things you can look for in minerals that distinguish them one from another. And I often get stumped when I'm out in the field. Sometimes I just don't know what kind of mineral it is. And so you can always rely on your observation. So if I don't know what the mineral is when I'm out doing field work, I might write down all the properties I can identify, and then later I can look it up, right? I could figure out, okay, it had this kind of luster, this kind of hardness, just making the observations that will help me identify it later on. So we'll start with color. So color is really good for some minerals. but not so good for others. A good example of that might be the mineral sulfur. So sulfur is always this yellow color. It also smells kind of stinky like rotten eggs. That's sulfur. This mineral here, galena, is always this silvery gray color. Here's another sample of it right here. So this color is almost always diagnostic to that specific mineral. But then we get minerals like quartz, and these are all, in this little cluster over here, these are all samples of the mineral quartz, and they all can vary somewhat in color. So we can see that there's crystalline quartz, so quartz that is essentially colorless. Okay, so that would be pure quartz, colorless quartz. A lot of people say clear, but clear is not a color. This would be colorless. This sample here has no color to it. Okay, here we have a piece of purple quartz. This is what's often called amethyst quartz. So little impurities in the mineral can impart the color. And a good example, or I guess an analogy for that would be, imagine a 5-gallon bucket of water, right? So you got a 5-gallon bucket of water, and what color is the water? Well, the water, like this little mineral here, is colorless, okay? It's also transparent, you can see through it. But what if I put 1 drop of red food coloring into that 5-gallon bucket of water? Just 1 drop. 1 drop of food coloring will impart some color to that entire 5-gallon bucket of water. And so that's the way to think of these impurities. This is pure quartz. This is quartz that's nearly pure, but it's got a little bit of something, and I don't know what the element is that makes it purple. Someone else out there might know. But it gives it a little bit of color by having a little bit of chromium or titanium or something like that. Other varieties of quartz, we have rose quartz, which is pink. This is sort of typical quartz you might see. This is milky quartz, kind of white, and then smoky quartz. And I'll spend a whole series on quartz because there's a lot of other varieties besides that. So color is always a good property to look for. Another property we often look for is luster, and that is either metallic or non-metallic. So how does the mineral appear in reflected light? Meaning, does it look like a metal or does it not look like a metal? And a lot of students get confused with this because they think this is shininess or not shininess, but really that's not what it's about. This mineral here, I think you can see, is reflecting the light. It's exceptionally shiny, but it's actually kind of colorless, or at least kind of white to colorless. I can see my finger through there. It's a little bit translucent. Light is passing through it. So this would be a non-metallic luster. But then we have minerals that look like metals, right? So this kind of looks like gold. So this has a metallic luster. This is the same thing here, metallic. Obviously this big piece of galena, kind of silvery looking. This piece of graphite, also metallic luster. And then maybe this one here. Yeah, this one here also has a little bit of metallic luster in it, although some of it's kind of turning brown. And we'll get to this one later. This one's got an interesting history. But all the rest here are non-metallic. Even these shiny ones over here are actually, if you look at them, they're transparent, they're colorless. These are non-metallic. They do not look like metal. Metal would look like the back of this chair here, silver, gold, jewelry, brass, copper, that sort of thing. Okay, so our next one is hardness. How resistant is the mineral? Depending on what it's made out of, it will have a certain hardness. Basically, it's resistance to abrasion. And I didn't put the fancy, you can look this up on the internet. There's a scale we often use from 1 to 10, 1 being the softest or nearly the softest material, 10 being the hardest. Most of you know this is diamond. This is a mineral called talc. So there's sort of a gradational scale that we often use to judge or quantify a mineral's hardness. And this is named after a gentleman with the last name of Mo. Don't remember his first name, but you can look this up on the internet. So this might be helpful, but the idea is that each mineral can scratch either another or a common household item. So in my classroom, the thing we often use the most to determine how hard a mineral is a simple little piece of glass. And this has a hardness of about 5.5. And so we can sometimes figure out how hard the mineral is by putting it down on something solid. Let me see if I can do this with 2 hands while I'm operating the camera. Put the mineral down there and then, sorry, that looks terrible, sorry. But you can see it left some scratches there, right? I can feel the grooves there. So this mineral here, which is quartz, is harder than the glass plate. So therefore it has a hardness of over 5.5. That's the hardness of glass, is about 5.5. A steel nail has a hardness of, I think, 4.5 or 5. A penny, a copper penny, You can look all these up online. There's all sorts of little hardness tables, that sort of thing. You can also take minerals and scratch one against the other and see how well they do. The other thing we often use in class, if we think it's potentially quite soft, is you can also test the hardness of a mineral by using your fingernail. So you can see there, as I drag my fingernail across, it's actually leaving scratches on this mineral. So this mineral, your fingernail has a hardness on the most hardness scale about 2.5, so this would be softer than that. This one's about 2. This is a mineral called gypsum. Let's see what else. Other physical properties we look at, crystal form. So every mineral has a specific crystal shape, specific geometric shape. The problem with using crystal form is that crystals tend to be quite rare. So you're oftentimes not going to find quartz that looks like this, right? This beautiful hexagonal, if you look at it from end on, you can see it's sort of a hexagon, 6-sided geometric shape. This is a quartz crystal, okay? Here's an aggregate of a bunch of quartz crystals, right? So these are nice. These are nice ornamental items. This might fetch, $10, $20 on eBay or something like that. But that's not often how you find it. Quartz is more often found kind of looking like this. No crystal faces, oftentimes not colorless, and so not nearly possibly as attractive, and therefore crystals forms aren't as helpful to identify. In order for crystals to form, what you need is you need some sort of cavity. So you need some sort of void or pore or hole in the rock in which the crystals can radiate out and grow into that cavity. So here's a nice geode with some lovely little crystals sparkling on the inside of this geode. But remember, this is the exception. Mostly nature gives us things where minerals are all squished together and we don't get these beautiful crystals. So crystal form, handy to know if you think you have a crystal, but probably not super helpful when looking at different minerals. This property is really important because this is the way the mineral will tend to look, especially as we see it in rocks. So this is a property called cleavage or cleavage planes, and it's basically how the mineral breaks based on its atomic configuration. So most minerals will have a tendency to break along planar surfaces. And what we're looking for to even tell if a mineral has a cleavage plane, because remember, some minerals might have 0 cleavage planes. If you hit them with a hammer, they just break randomly. Other minerals tend to break in certain shapes, whether it's cubes, it could be more prismatic shapes, kind of long and elongated. It could be that the mineral likes to break into sheets, right, or planar type of configurations like we have here. These minerals tend to break into sheets. And so what we're looking for when we're looking for cleavage planes is it's got to do both of these. It has to be a somewhat planar surface. So the mineral should have surfaces, maybe more than one, maybe only one, just depends on how many cleavage planes it has, that also reflect light. A good cleavage plane does both of these. It is a somewhat planar surface and it has some reflective properties. Cleavage planes can vary from really awesome and quite impressive to cleavage planes that aren't as well defined, okay? But this will influence the shape of the mineral in the rock, and that's why it's kind of important. So, for example, quartz, if we pick up our more common piece of quartz, a non-crystalline form, and I rotate this in the light, you can see that there's a little bit of reflection in there, but none of the surfaces look very planar or flat. They're kind of irregular, and there's just not a reflective quality there. So this would be an example of a mineral that has no cleavage planes, good old quartz. If we move to minerals that have one cleavage plane, we could look at either this piece. These are actually 2 minerals in the same family. These are the micas. This is muscovite, this is biotite. But we can see that these break into nice, thin sheets. I can't do this with one hand, but if I had 2 hands available, maybe I can do it. There we go. So I actually peeled off one little layer there. And so you can see that this mineral has a tendency to break into sheets. So this would be a mineral that has one cleavage direction. It's going to preferentially break along that surface. And we can see that surface is exceptionally reflective. Cleavage planes don't get much more reflective or perfectly planar than a good piece of mica, either biotite, muscovite, or there's some other micas as well. Gypsum, same thing, breaks into sheets. If you look at the edge here, not a lot of reflective quality there, but definitely on this large side, it's much more reflective, and on the back side. So even though there's 2 sides there, those sides are parallel, so we would say it has one cleavage plane. My thumb and my forefinger are touching two parallel sides, but that only counts as one cleavage plane. So essentially what we're looking for with these cleavage planes are non-parallel planes. If we bump up to two cleavage planes, this piece of potassium feldspar is a great example of that. You can see a very planar surface up here, very reflective, and then a nice edge right here. And then as I move over to this side with my thumb, you can see another beautiful cleavage plane as well. So here we have 1, 2 cleavage planes. They are not parallel to each other. And in this case, they intersect and make an angle. And if you look right down with the cleavage plane on your right and on the top there, you can see it makes a nice 90-degree angle. So we would say this mineral has 2 cleavage planes that intersect at 90 degrees, okay? Notice over here, not much of a cleavage plane and not as much here, although some of these are parallel, so you might be catching some of that as well. So 2 cleavage planes at 90 degrees for that one. What about if we have 3 cleavage planes? This lovely piece of galena is a good example of that. A little heavy to hold up, but we've got 1, 2, 3 sides, basically a cube. There we go. Forming these cleavage planes, right? So we can see this surface is pretty shiny. It's not perfectly planar, but it's nearly so. And we can see that even if you get in here close, a lot of these little surfaces are little parallel planes to this larger surface, right? Rotate this one over, nice big plane. It's reflective, it's fairly planar. There's another one there. So even though it's a cube and cubes have 6 sides, we would say that this mineral has 1, 2, 3 cleavage planes. Remember, they're non-parallel cleavage planes. This plane is different than this 3-dimensional plane, different than this one. And look here how they intersect at a corner. So if you have 3 cleavage planes, you'll oftentimes get a corner intersection, whereas if you have, back to this one, 2 cleavage planes intersecting, you get more of an edge, like an elongate edge, like that one. So the galena has 3 cleavage planes. Another one over here is calcite. These are all pieces of calcite right here. These look somewhat like a cube. You can see the reflective surfaces. They're very planar. But if you look at this closely, remember a cube will have 90-degree intersections, right? So we've got a 90-degree angle right there between those 2 planes. As we look at this piece of calcite and look at it kind of end on, you can see down here by my pinky that the intersection is not quite 90 degrees. That is a smaller angle than 90 degrees, an acute angle. And so this shape kind of looks like a squished box. It's not quite cubic in shape. This is what we call a rhombohedron. So this mineral then would have 3 cleavage planes, same as the cube, but instead of intersecting at 90 degrees, these intersect at a non-perpendicular angle, not 90 degrees. Okay, so that's calcite. We can see a little bit of variability with the color of calcite as well. This one's kind of yellowish to colorless. It's also transparent to translucent. This one's got a little bit of a purple, pink hue to it. And this one's more, I guess, more whitish. But those are all pieces of calcite. Let's see what else. So 3 cleavage planes. This is a piece of fluorite. This mineral has 4 cleavage planes. So if you look at its shape, it kind of looks like 2 pyramids put base to base, or another name for this shape is an octahedron. So it has 8 sides, but only 4 cleavage planes. So my forefinger and my thumb are on parallel planes. So that's 1 cleavage plane. This one's parallel to that one, so that's a second one. I'm running out of fingers here, but you get the idea. So you'd end up with 4 cleavage planes if you actually counted all of those. We can also see with the fluorite in this little box that color varies, right? We've got colorless, a yellow piece, a blue one. It's often pink and purple as well, so a little bit of variability in color. So hopefully that's kind of helpful. A couple other quick properties that I just thought of is magnetism. There's not a lot of magnetic minerals, although when you get into ore minerals, you can find some that are magnetic that way, but here's a mineral that attracts the magnet. This one is called, this has a great name, right? A magnetic mineral. What would be a good name for that? This is magnetite. This is essentially iron that oxidizes. So if you're looking at some of this reddish brown particles in here, and you're like, gosh, that looks like rust. Well, that's what this is. This is what happens to iron when it becomes more oxidized, when it gets oxidized over time. It kind of gets this reddish, this orangish brown color. But it's a naturally magnetic mineral, okay? It attracts a magnet. And then the only other property I want to throw in here, in geology class, we often use these fun little dropper bottles of like 10% hydrochloric acid. It's a weak acid. It's not going to burn your skin per se. It's not going to cause your skin to peel, but it could burn a hole in your clothes. I think you can also use vinegar. So if you can't get your hands on some dilute hydrochloric acid, you could use some vinegar. But there is a mineral, and this is an important mineral. This is calcite that will react with the acid. And we also find it in some rocks. And so we'll spend some time with that when we get to rocks, but you can, just for fun, you can see the reaction. And what it's doing there is it's reacting with the carbonate, the CO3 in the rock, and releasing CO2. So there's a chemical reaction. Basically what's happening is that mineral is being dissolved by this weak acid and causing those chemical reactions to occur. So this is a handy little tool that we oftentimes use in the field to identify minerals as well. You can see there's several minerals, like the quartz, kind of whitish. We've got the calcite, kind of whitish. The gypsum, maybe the fluorite. There's several, and there's a bunch of others as well, that are kind of the same color. So you can see how these properties are important to distinguishing one from another. So hopefully that's a good crash course in physical properties of minerals. We'll use this to set the stage for the next series of videos I'll put together, which is focusing on either one or two specific minerals and kind of diving into them deeply. I'm also going to try to include the mineral as you see it in nature. So rather than some of these really nice, crystal pieces and museum quality pieces, I want to show you more of the kind of grungy material and the things you might encounter more when you're out on your little explorations, looking around, that sort of thing. So hopefully this was helpful. A fairly short crash course into minerals and physical properties of minerals. This should help get you acclimated to these, and that way when we move forward with the next couple of videos, we talk about cleavage planes or luster or something like that, you'll be on board. So hopefully people enjoy these. They're fun to make, and I will see you next time with a new mineral, and we'll look at our first set of minerals. So enjoy.